So then next speaker will be Antoni Lopez-Martinez. The title of presentation is the solution to a problem in linear chain recurrence. If you're ready.
Okay, well, so I'm going to talk about a solution to a problem in linear chain recurrence, and this talk is based in a joint work with Dimitris Papatanasiou from Savansi University. This work has been published recently in 2025 in the Journal of Differential Equations. And here, well, you can see some of the sponsors of this work. But okay, let's go to the important part, which is the talk. I have divided it in 3 parts. First, I will introduce the topic, and I will pose the problem that we wanted to solve. And then in the second and third part, we will solve the problem first with shifts on trees and then using an invertible counterexample. Okay. So let's start by the introduction. And okay, we are studying linear dynamics, and linear dynamics is the combination of operator theory and topological dynamics. Okay. So we always have xt, a pair, which is called a linear dynamical system, where x is a Banach space, usually infinite dimensional, and t will be a continuous linear operator. Okay, so in topological dynamics, sometimes what they do is considering x just as a metric space and t as a continuous map. And in fact, sometimes this metric space is compact, as we will see along the talk. Which kind of properties are studied here? Well, in linear dynamics, we have properties such as hypercyclicity. This property comes from the property of studying dense orbits in topological dynamics. We also have different notions of chaos that also come from topological dynamics. And it has been studied, the notion of frequent hypercyclicity, which is hypercyclicity mixed with some notions of recurrence. Okay, so this also comes from topological dynamics, more or less. And in fact, in topological dynamics, many other notions have been studied, and now they are starting to be included in linear dynamics. Okay, so in this talk we'll go in this direction. So we are not going to talk about shadowing and hyperbolicity, but a related notion, which is chain recurrence. Okay, so in order to introduce chain recurrence, first I need to introduce what is a delta chain. So a delta chain from a vector x0 to xm is a finite sequence of vectors, such that whenever I take the image of any of these vectors, then the next one in the sequence is just a delta perturbation at most of the image of the previous vector. Okay, so I take x0, I take its image, and then I can perturbate this vector at most delta. So I take the ball centered on t of x0, and I pick any vector inside of this ball to be x1. And then I continue this process. So I take the image of x1 and I consider another vector x2. Okay, so this is what is called a delta chain for a positive delta. And once we know this definition, then we say that a vector is chain recurrent if for each delta there exists a delta chain starting and finishing on this vector. Okay, so recurrence means that I can come back to the vector, and chain recurrence means that I can come back to the vector with chains. Okay, so we will denote by CRT the set of chain recurrent vectors of an operator, and we say that a dynamical system is chain recurrent if every single vector of the space is chain recurrent. Okay, so the thing is that this notion has only been studied in linear dynamics from 2022. In fact, the first paper focused on this property was from Antunes et al. In 2022, and then there is another paper in 2024 talking about these kind of properties. So I would like to present some of the main things that this property fulfills, which are the following. Okay, so one can use chain recurrence to study previous notions studied in linear dynamics, and in fact, in these papers, it is proved that when you have a chain recurrent operator that has positive shadowing, then the operator is topologically mixing, frequently hypercyclic, and in fact, it is densely distributionally chaotic. So you can study chain recurrence from the perspective of relating it with previous properties studied in linear dynamics. And then I have to introduce two more properties that I will need along this talk, which are the following. A vector is chain recurrent if and only if for each delta, I can find a delta chain from x to the zero vector, and then another delta chain from the zero vector to x. Okay, so one of these implications is almost trivial because what I want to do is, okay, I have a chain from x to zero, and then I have a chain from zero to x. So I just have to concatenate both chains to get a chain from x to x. Okay, and this is what I will need for the rest of the talk. Okay. And then there is another property, which is main property, which is that the set of chain recurrent vectors is a t-invariant closed linear subspace of X. So once we have an invariant subspace, we can consider the restriction. So this is the problem that we wanted to solve and the problem that we are going to solve in this talk. Bernard de Saint-Péris in 2024, they asked what happens to the restriction of the operator to this subspace of chain recurrent vectors. Okay, so what they asked is the following. We have an operator, we restrict it to the set of chain recurrent vectors, and the question is it true that this restriction is again a chain recurrent dynamical system? So the idea is, okay, we know that for each vector in this set, and for each delta, okay, there is a delta chain that comes back to this vector. But the question is if this delta chain is necessarily inside, I mean, if it can be taken inside the set of chain recurrent vectors, all the elements of the chain, or if you necessarily have to go outside this set to construct this chain. That's the question, okay? So, what was known about this problem? Well, there are many situations in which the answer is yes, that when you take the restriction, it is again a chain recurrent dynamical system. And in fact, here we also have examples of non-linear dynamical systems. When we have consider T as just a continuous map, and for instance, if the space is a compact metric space and the map is an homeomorphism, then the answer is yes. Then the restriction, the set of chain recurrent vectors of the restriction is still the same set than the set of chain recurrent vectors than the original map. Okay, and in linear dynamics we have cases 2 and 3, which is that okay, if X is a Hilbert space and T is a self-adjoint linear operator, then the answer is again true. And then if X, more generally, if X is a Banach space and the set of chain recurrent vectors admits a T-invariant topological complement, then the answer is again yes. Okay, so of course case 3 is a particular case of case 2 because of the Hilbert space, the projections, and the self-adjoint property. So we had many positive cases, and that's why they asked this question. And the question is negative, and the answer is negative. Okay, so what we do in this work is proving this theorem, which tells you that you can construct a Banach and even a Hilbert space and a continuous, and even if you want invertible linear operator on this space, such that the set of chain recurrent vectors of the restriction to the set of chain recurrent vectors of the original operator is exactly the zero vector, while the set of chain recurrent vectors of the original operator is non the zero vector, is much bigger, and in fact it can be taken infinite dimensional, as we will see for the rest of the talk. Okay, so this is the introduction, and now I would like to go to show the counterexample that we constructed, because it's not complicated and it's more geometrical than everything else. Okay, so let's see a counterexample using shifts on trees, and I have to start saying that when you ask a problem to a person that works in linear dynamics, the first thing that he does is trying to think on shifts. Okay, but the thing is that classical shifts, classical backward shifts, weighted backward shifts, are not enough to solve this problem. Okay, so this is the Banach version of a theorem of two theorems from Bernard de Saint-Péris. The first one was for unilateral shifts, the other one for bilateral. Here we have both statements mixed. And the thing is that if you consider B as N or zeta, unilateral or bilateral, and then you take the C0 or the LP spaces associated to this set B, then you fix W, which is a sequence of weights, and you consider the backward shift, which simply the coordinate xn goes to xn, well, xn minus 1, right? Xn minus 1 multiplied by the corresponding weight. Then these two things are equivalent, okay? So they characterize chain recurrence, which I recall means every vector in the space is chain recurrent, with some properties that the weights have to fulfill, okay? So here you have an image that explains what's happening with this kind of operator. So if we had the unilateral case, then you just forget about this left side and you just look the operator until E0. And then, okay, so each element, each value goes to the left multiplied by some weight. So the thing is that in our paper, what we proved is another equivalence to these two equivalences, which is that, in fact, whenever a backward shift of this kind admits a non-zero chain recurrent vector, just one non-zero chain recurrent vector, then you have these two properties. In fact, what we prove is that 3 implies 2, and then 2 is equivalent to 1. So we cannot get a counterexample for our problem with classical backward shifts. So we had to modify and do something. And this is where the trees are coming to save us, okay? And the thing is that I'm not going to define exactly what is a directed tree, but with this image, you more or less can imagine what is a directed tree. So I just have what we had before, which is a level with elements indexed in zeta, and then I have some extra branches, and this is what is more or less a directed tree. Okay, so I just consider zeta and the indices minus kj that are these extra branches that we are putting in this left side of the tree. Okay, and then you can consider any of the Banach spaces LP. In fact, Hilbert for p equals 2. The same thing happens for C0. There is no problem with C0, but I didn't have enough space to include all the things. So you consider this Banach space or Hilbert space, and now you consider a shift on this tree, okay, which simply moves the values to the left in the zeta level, multiplying by mu1, and then in these extra branches you multiply by mu2, okay? You have to take that the modulus of mu2 is greater than mu1, and that's all. This is going to be our counterexample, okay? So how to prove that this is a counterexample? So the idea is that for this operator, we will have the equality that the set of chain recurrent vectors is exactly the closure of the span of the elements of the canonical basis sequence associated to the zeta level, so in this level, okay? So if we prove this equality, the restriction is going to be a classical backward shift. And in fact, this classical backward shift has only the zero vector as a chain recurrent vector, because he's not fulfilling the properties that we were stating before in the characterization of backward shifts, okay? So the thing is that if we are able to prove this equality, we are done. And how to prove this equality? Well, the idea is the following. Let us go in two inclusions. So first, we show that this thing is included in the set of chain recurrent vectors, and the idea is exactly this is the same for every vector here. You just take any element. In fact, for this example, I'm going to take E1, and then you do the same computations that I'm going to do now, and you can show that E1 is included there. So since this is a subspace and a closed subspace, then you get the conclusion, okay? And the idea is the following. So we start from the vector E1. So I have some value in this point in this position E1. Okay. Now I'm going to construct a delta chain. So I take the image and I go from E1 to E0 multiplied by mu1. So this black part of this vector is what we get just applying the operator. And now this blue part is the delta perturbation that I'm putting here. And this delta perturbation, this will be a delta perturbation if k is big enough, because mu1 has modulus greater than 1, okay? So then what I'm doing is putting some perturbation just here in this point, in the minus kk vector. And now you just have to apply k times the operator, so that the value that we have put it here, it's coming down, and the value that we have in E0 is coming to the left, so that they collapse in A minus K, and you get the zero vector. So you have a delta chain from E1 to the zero vector. And then To construct a delta chain from the zero vector to E1, the only thing that you have to do is to consider a enough right element like EK and to put some perturbator, some delta perturbation here. Of course, mu1 has modulus greater than 1, so when k is big enough, this is a delta perturbation, so that you go to the left and you arrive to E1 and you recover the vector E1 by applying the operator. Okay, so this would be the proof of this inclusion. The other inclusion is a bit more technical, and I'm just going to explain it with simple words. And in fact, the idea is that if you have any vector that is not included in this linear span, then you have some coordinate outside of the zeta level, so in some of these branches, that is non-zero. And the thing is that if you take a delta small enough, then you cannot find a delta chain finishing in this vector. Why? Well, imagine that you had the non-zero element in this coordinate here. Whenever you apply the operator to some vector, then here you get a zero. So whenever delta is smaller than the modulus of this coordinate, then you cannot arrive with a delta chain to this vector. So this is more or less the explanation of this inclusion. Okay, so for the moment, everything is simple math. Everything is very geometrical, and we were very happy because we had solved this problem. And we went to Nilsson, Bernardes, and Peris, who posed the problem, and we told them, okay, we have solved the problem. And they said, okay, very nice, but can you give an invertible counterexample? Because if you remember, for compact spaces, the result is true when you have an homeomorphism. So they really wanted to have an invertible counterexample. And this is what I would like to present in the last 2 or 3 minutes of this talk. I'm not going to give all the details, but the idea is to modify the counterexample that we have just presented in the second part of the talk. And in fact, this is the counterexample that we had. Okay, so we have here what is called a backward shift, a weighted backward shift on this tree, okay, on a directed tree. And the final result followed by this equality, by showing that the set of chain recurrent vectors is exactly the linear span of the zeta level, which are the vectors that we have here. Okay, so okay, to have an invertible operator, here we have some problems because this operator is not injective. In fact, for instance, from E0 and from this vector, you are arriving to E minus 1. So you can construct a vector that is non-zero whose image is 0. So it's not an injective operator. And it is also non-surjective because for every of these coordinates, when you take the image of the vector, then you get a 0, okay, here. So you cannot recover a vector that has a 1 in this position, okay, with an image of another vector. So which is the idea? So the idea is going to put infinite branches here. So we are going to consider this modification of the operator. So we still have in the zeta level a backward shift. And then we have infinitely many backward shifts that are bilateral. And we respect the weights that we already had. But then we put some different weights there to compensate what these weights are doing. So we extend these branches infinitely down and infinitely up. And this is what I called a hammer. Okay, so you can take the hammer from this part. You can take a hammer. This is a kind of hammer. And the idea is that this is going to serve as a counterexample as soon as we consider W, which are the weights that we have to put in the extra branches that we have added now, as a bounded from above and bounded from below sequence, such that the respective backward shift, bilateral backward shift, only has the 0 vector as chain recurrent vector. Okay? And the thing is that once you consider this thing, then the modified operator, this is not longer a backward shift on a tree, because backward shifts on trees are just invertible if they are bilateral and classical shifts, but you can still prove the same property, that is that for this modification of the operator, the set of chain recurrent vectors is exactly the linear span of the set of the zeta level. Okay, and then you get the same proof than in the previous case, and this one is invertible. Okay, so this is everything what I wanted to explain. And in fact, let me just conclude recalling what we have seen. Well, in part one, I have introduced chain recurrence in linear dynamics, and I have posed the problem that we have solved. Then in part two, we have seen that using shifts on trees, you can answer the problem, but for classical shifts, you cannot do it because you will have every vector being chain recurrent whenever you have one vector that is not chain recurrent, that is chain recurrent, sorry. And then in part three, we have solved the invertible case with a modification of the backward shift on a tree case, which was the very first simple idea that we came out with to solve this problem. And then we have fully proved the theorem that we wanted to prove. Okay, so I would like to end the talk by leaving this question from Antunes et al. In 2022. Okay, they asked which condition on a subspace, okay, so Y here is a closed subspace, guarantee that the restriction of the operator is chain recurrent. So this is a question that they already had in 2022. And the only thing that I want to do is that our work shows that you cannot answer this question even for the moment, okay, even if you assume that the subspace Y is the set of chain recurrent vectors of the original operator, which was probably one of the best chances to get a solution to this problem. Okay, so this question is still open, and in fact, our theorem proves that it's going to be complicated. So that there is a gap, and many theory probably can be done in this direction. And well, that's the end of the talk. Here you have the references. And as I said, this is based on this publication in the Journal of Differential Equations, a very recent publication. And that's all. Thank you for your attention.
Thank you very much for your talk.